everyone, welcome to the next session of Strength of Materials. In this session, we are discussing a numerical on composite bars. They are also called as bars in parallel. Let's start with the numerical now. A compound bar shown in figure below consists of a 30 mm diameter steel rod encased in a copper tube of internal diameter 30 mm and external diameter 40 mm. So when I look here, these are the bars which are in parallel. The internal one is of steel and the outer one is of copper. You can see the top view of this diagram here. So the inner one is steel, outer one is copper. Now if you observe carefully, the inner one is a solid bar which has diameter 30 mm as given in the question. So I'll start with the data given in the question. That is diameter of steel rod. Let me call it as DS. This is given as 30 mm. Since the diameter is known, I can calculate the area. Say I call it as AS. It will be pi by 4 ds square, which will be pi by 4 into 30 square. Okay, I'll leave it in terms of pi. So this will be 225 pi mm square. Next is given the diameter of, okay, that too internal diameter. There are two diameters for copper. So I'll write down internal diameter of copper rod. Say I call it as DC is given as 30 mm and the external diameter of copper rod, say I call it as capital DC, it is 40 mm. So the area of copper rod will be pi by 4 DC square minus small dc square. So this will be pi by 4 into 40 square minus 30 square. On solving this, I obtain 175 pi mm square. Now if you look at this diagram, the total length of these two rods, because they are combined together, so these two rods have the length of 800 mm. So let me write down length of copper and steel rods. Both will be L and it is given as 800 mm. Find the stresses produced in copper and steel, which means I need to calculate sigma S and sigma C when a load of 100 Newton falls from a height of 40 mm. 40 mm is going to be my height from which the load is falling, and the value of load P is given as 100 Newton. So you can see in the diagram, this is the load which is attached here. This will fall down, whose value is 100 Newton, and the height is 40 mm. The value of Young's modulus of steel and copper both are given to me. So I can just write down that the weight which is going to fall, it is P, is given as 100 Newton. The height of fall, H, is given as 40 mm. Value of ES is given as 2 into 10 raised to 5 Newton per mm square. And the value of EC is given as 1 into 10 raised to 5 Newton per mm square. Next I'll write down to find, I have to find sigma S and sigma C. Now let's start with first writing down that let sigma S is the stress produced in the steel tube or steel rod, whatever you say. And sigma C will be the stress produced in the copper rod. Now, since both the ends are fixed together, I can say that the strain you can see here there is a fixed line, and obviously this is also a fixed line on which the load is going to fall. Therefore, I can say strain in steel rod will be equal to the strain in copper tube. You can write this rod as tube because that's what is given, and it's actually a tube because it's hollow. It's not a rod. So you can write this as sigma S upon ES, which is equal to sigma C upon EC. Therefore, I can say sigma S is equal to ES upon EC into sigma C. When you substitute these two values, you can see here it is 2 into 10 raised to 5 upon 1 into 10 raised to 5. The 10 raised to 5 gets cancelled from the numerator and denominator. So what remains is just the value 2 into sigma C. So I can say that sigma S is twice sigma C in this question. I'll mark this as equation 1 in case I require it further. Next, let's calculate the total strain on the body. We know that strain energy stored in steel rod, say I call it as US, will be given by sigma S square into AL upon 2E. Thus E is ES, A will be AS. L is same for both the material. So I can write here it is twice sigma C as we got from equation 1, the whole square into AS is already known to us, it is 225 pi, L is known as 800 upon the value of 2 into ES. So it is 2 into 2 into 10 raised to 5. When I solve this, I get 5.6548 and the sigma C is also there here, so it is sigma C square. This is the value of US. Let me mark this as equation 2. Next, let's talk about the strain energy stored in the copper rod. It's copper tube, so let me write it as UC is sigma C square into AC into L upon 2EC. Sigma C can be left as sigma C. This value is 175 pi. L is 800 upon 2 into 1 into 10 raised to 5. When I solve this, I get 2.199 sigma C square. This is the value of UC. Let's take this as equation 3. Therefore, total strain on the body can be calculated as US plus UC, which is the addition of equation 2 and 3, which you can see here. So when I add equation 2 and 3, I get the value as 7.8539 sigma C square. Let's mark this as equation 4. If you want, you can write here from 2 and 3. Now, next let's talk about the work done by the falling weight. We have already discussed the formula. It is P into H plus delta L. Here if you want, you can also write delta Li. I am leaving it to delta L. Now here we know the value of P is 100, H is 40. I don't know what is delta L, so I'll leave it to this and I'll mark this as equation 5. Now I know the formula for strain in copper tube. We have already studied this. The formula is sigma C upon EC. If you can recollect, we have discussed this in the chapter of stresses and strains. This is the formula of strain. Also we know strain can be written as change in length upon original length. So this will be sigma C upon EC. Now therefore delta L can be also calculated as sigma C into L, which is 800, and EC, which is 1 into 10 raised to 5. When I solve this, I get 8 into 10 raised to minus 3 sigma C. Now this is the formula for delta L. I can mark it as equation 6. Now I can substitute this formula of 6 in this equation of 5. Therefore, I can say work done is equal to 100 into 40 plus 8 into 10 raised to minus 3 sigma c. Let's mark this as equation 7. We have just studied in the previous session that the work done is always equal to the total strain energy. So I can equate equation 4 and 7. I'll write down, since work done is equal to total strain energy stored in the body, therefore I can say 100 into 40 plus 8 into 10 raised to minus 3 sigma c will be equal to total strain energy, that is 7.8539 sigma c square. From these two equations, when you substitute in your calculator, you will get the value of sigma c as 22.6185 Newton per mm square. I know that sigma s is 2 times sigma c. You can see in equation 1 we have found this. So right here it is from equation 1. Substitute 2 into 22.6185. The answer will be 45.237 Newton per mm square. This is the answer of sigma s. With this, I'll end the session. I hope you have understood the numerical. If you have any doubts, please write to me in the comment section. See you in the next session with some more concepts on strain energy. Thank you.